more than 20 years in research. So today I want to give you an overview of the 5G networks. And I would like to start with a bit of background, so about innovation, about openness. So if we look at different industries, both computing and in this case mobile networks, we can see that everything started with a very specialized system, very integrated system, very monolithic. So the main reason is that at the beginning, all this technology is pretty new, is quite demanding in terms of performance and in terms of functionality. So all the starting point requires a very tightly integrated system. So that's why both in computing and then in mobile networks, they started with a huge setup, hardware, fully integrated with operating system, and fully integrated with the applications of functionality that are built on top of that system. But then that means that only few vendors are able to deliver this kind of system. So that's becoming a closed ecosystem, a closed environment. So what happened with the computing, we saw like creating open interfaces between the hardware, operating system, and the applications. Then that brought innovation, that brought new set of applications, new set of functionality that then delivered like a more multi-vendor environment. So the same thing repeats in the mobile network. So basically we saw that the mobile phones, they were fully integrated, the hardware, the software, and so on. But then over time, then that system becomes open. And then all the interfaces are available for third-party developers. And that then delivers more applications, more innovation. And in all the Facebook and YouTubes wouldn't be possible if this kind of openness wouldn't have taken place. So in that sense, we need to, or at least this kind of innovation is associated to breaking down all these monolithic systems into more distributed and then building open interfaces. So then new applications, new services can be deployed on top of those commodity systems. So that's what has been happening in mobile networks. So if we look at the first releases of mobile networks, 1G and 2G, we see that there were tightly integrated functionality. So we had the base stations that were all then fully connected to a base system controller, and then there were few components that were managing all the user authentication, connectivity, and then also storing all the data, user data, into what is called HLR, home local registry, and all this functionality was running in a few boxes, like a base station controller and the mobile switching system, so the MSC and then the database. So this was required because at that point, all these 5G networks, all these mobile networks, they were quite complex, and then it had to be fully integrated as a monolithic system. So in that sense, if we go through those different generations, we see that at least the main difference between the first generation and the second generation was the digitalization. So basically, first G or 1G, it was more like analog type of networking or mobile networks, and then 2G became sort of digital. So in that sense, all the communications were becoming like digitalized. So all the data processing and all the communications were becoming like digital. The other thing is that 2G was still circuit switch. So basically, you need to think that all these mobile networks were deployed on top of the fixed network. So that means that at the beginning we have the fixed mobile or the fixed telephony, and then on top of that, then we design the mobile network. So in that sense, the 2G, it was still built on top of this switch network, and that's what the GSM, the first global mobile infrastructure, was based on. So in that sense, if we continue in this sort of evolution, we see that then, okay, we first move from analog to digital in the communications. Then in the 2G, we still have the circuit switch. The other thing is that one of the big achievements of the 2G is that become global. So basically, that's associated to openness and standardization. So that means that if we have a system that can be deployed by the multiple vendors, then can be installed in a global setup. So basically the ecosystem becomes larger than if it's monolithic, it's integrated, and only few vendors can deliver that system. So that was one of the major achievements: globalization, digitalization, globalization of the mobile networks. Then after we have this sort of evolution, then the next thing was the internet. So at that point, the mobile networks were still built on top of this circuit switch. It was digital, but still built on top of analog transport. But then it comes the internet, it comes the IP protocol, and that's first again was adopted in the fixed network. So all the communications on top of the mobile networks were moving from this sort of more like sort of circuit switch into IP type of routing and communication. So at that point, we had to design like a new components, a new sort of translators. So basically, the communications were still built or based on this circuit switch, but then on top of that, we have the IP packets, and then we had to define what is called the general packet radio services and gateways, which basically were receiving the normal mobile communications, and then inside that, it was coming all the IP communications. So in that sense, we started moving from this 2G architecture, where we have the mobile station or the equipment, which is the one that it has the SIM card, and then that system was then renamed in 3G into user equipment. So it was becoming more like a user device instead of like a plain mobile station. Then also the base station and the base station controller, which was taking care of all the radio access, that was changing also in the 3G. So then that was evolving, and then a new set of radio components were defined in order to manage all this handover and mobility between different base stations. Then also the mobile switching center, the MSC, which is the smart or the intelligent part of the mobile network at that time, that was originally was a circuit switch. Then that part then was also breaking down into smaller pieces. So basically we will see that all these main components that in 2G were taking care of everything, over time these modules has been breaking down into smaller pieces, into a smaller functionality. So in that sense, the first thing we did is that connecting this mobile network into the fixed network. So basically, the idea is that we have the circuit switch, which is the fixed mobile fixed network, and then we had to connect that to the mobile network. So then this kind of interconnection was done by the gateway, some MSC gateway that then was receiving all the communications and then connecting that to the public switch network, to the fixed network. And then all the user data and user information was kept in a set of databases, which then were storing all the SIM data, all the SIM information, like identity, subscriber. And then there were also a set of authentication procedures. So basically, one of the key things is that in 2G, it was becoming like digital. But then one of the key things is that the mobile network needs to be secure. So then we have all this SIM information that had to be registered and authenticated in the infrastructure. So in that sense, we see how this 1G and 2G was moving from this monolithic into more distributed. So basically, we see that they are breaking down into these interfaces and then adding this kind of different components. So this is how the 2G was evolving towards 3G. So we see that this BTS and BSC that was taking care of the radio now is managed by a new component, which is the radio network controller, which then is talking to the base station, which now is changed from BTS, base transceiver, into E-Node-B, enhanced node base station. And then we see that in the 3G, we are moving from a circuit switch to IP networks. So in that sense, in the 2G, that was these few components taking care of bridging all the communication with the fixed network, the public switch through this gateway. Now we have to add a new set of elements which are then receiving all the information from the mobiles and then encapsulating that or directing that to the internet. So basically, we had a new gateways, which is serving GSM, serving GPRS serving node, and the GGSM, which is the gateway that is bridging all this, the legacy type of mobile with the public internet. And since the communication were moving into IP, one additional component of functionality is the IMS. So basically, before, all the communications was done like over a circuit switch. So we have the fixed phones, and then we have the mobile phones, and then we have all the voice communicating with this kind of dedicated circuits. Now, in the 3G, we are moving into the IP type of network, into the internet. So in that sense, all these voice communications that were based on circuits links or communicated dedicated links now have to be built on top of IP type of protocols. So in that sense, a new component, the IMS, Internet Multimedia Subsystem, was designed. And this is one of the good examples of innovation. So basically, now this kind of internet type of protocols were not defined by the telecom vendors. This IMS was defined by the Internet Engineering Task Force. And in that sense, this is like a good case of innovation. So basically, this first sort of design of the IMS based on the session initiation protocol, it started from the ITF. And then it started, as you can see in the pictures, it started in a basement, in a garage. So in that sense, we see how these new services are not defined by the big corporation, but then are defined by small entities where, for example, as you see, we as Aalto University, or in this at that stage, it was Technical University of Technology, we were there. So we were sort of in the origins of this system. So universities and then sort of small companies and so on were the ones that were designing this starting of new technologies, IP systems or IP technologies for mobile networks. And now we see that, okay, we continue with this separation, with this sort of breaking down into small components, into different modules that take care of all the mobile functionality. And then in 4G, we see that there are new elements. So for example, we have the base station, which is the eNodeB. We have the mobility management, which before was the MSC. Now it's translated into the MME. Then we have the home location registry, which is the database, and now becomes the home subscriber server. But then we start adding new elements like the policy control. We have the serving gateway, within the 2G was the SGSN. Then we have the packet gateway, which in the 2G was the GGSN. And then we connect that directly to the internet. So basically, now we are defining this component, which resemble the previous ones in 2G. But then the other big difference is that now we are separating the signaling from the data. So from 1G to 2G, we have digitalization. We still have the circuit switch. 2G to 3G, we have IP networks. Now in 4G, we are separating the functionality. So we have components that take care of the signaling. So signaling means like when the device connects to the system, then it has to do all this user authentication, user registration. Then it assigns some set of policies, and this user has this amount of capacity reserve, or like have certain budget in terms of volume of data. And then the other thing is that the data itself, the data from generated, the user data, that then is separated through different components. So you see that the yellow lines are the signaling. Those are the ones that are taking care of all the SIM authentication policies and all that stuff. But then the blue line is straight coming from the device to the base station and then to the gateways. And from the gateways, then it goes to the internet. So that means that it's not anymore like separating the modules, but then also separating the signaling from the data. And that requires a new set of protocols. So basically, that means that we have to build a bit of a complex networking stack. So in that sense, we can see that the network needs to have first a set of protocols between the base station and the signaling. So we see that these protocols are based on IP technology. So as we saw, in 3G we are moving into IP. So now everything is based on IP. So that means that the baseline protocols are IP based. So we have layer 1, the physical layer, we have the Ethernet, and then on top of that we have IP. So basically communicating endpoints by the direct IP connection. And then on top of that, we need to have a protocol that is setting up all the flows, basically communicating the base station with all the network functions that are taking care of the signaling. And in this case is the streaming control transport protocol. It's similar to TCP, I mean transmission protocol, but then it has a new functionality required in mobile networks like multi-homing. So one of the key factors of the mobile networks is that it needs to be extremely reliable. So that means that the same protocol needs to be connected to multiple endpoints. So basically that's the multi-homing. So from one base station or one sort of radio system needs to be connected to a redundant set of network components in order to ensure high availability. So that's done with the SCTP. And then on top of that, we have the mobile specific protocol, which is the S1 signaling. And that one is structured in a set of information elements. In those information elements, we have the SIM information, we have user identities, we have what kind of radio is supported, what kind of devices are available. So all these information elements are part of the mobile specific signaling, which is the S1 protocol. And then that's transported over the SCTP to the endpoints that take care of the signaling. And then in this transaction, the MME, Mobility Management Entity, then after checking that, okay, this user is authenticated, is legitimate, then I can assign the IP address. So basically, at the end of the day, what we want is that the mobile will be assigned an IP address in order to communicate with other devices in the public internet, in order to access to all these internet services, YouTube, Facebook, or whatever. So all this process is happening as part of the registration, as part of the device attachment procedure. So then once we have this functionality, then it comes the data. So basically what we have is that the device has been authenticated, then it has been assigned an IP address. Now it can start sending data. So now this kind of procedure then is happening between the base station, the MME, and then the S gateway and P gateway, which assign the IP address, and then they can start sending all the data directly between the endpoints. And this is the user plane. So basically, now what we have is that the data is coming from the device, the user equipment, to the base station, the eNodeB, and then goes directly to the gateway. So that means that it's not the MME, the HLR, all those policy functions are not involved anymore. All this signaling has been completed successfully. SIM authentication has been done. And now the data from the device is coming through all the radio devices to the gateway, and then from the gateway to the public internet. But then the thing is that this data, the IP packets that you see on top of the networking stack, those IP packets are the ones that are generated from the mobile. But then those IP packets need to be encapsulated inside the radio specific, inside the mobile specific protocols. So on the radio part, we see that the IP packets are encapsulated into the radio link control and the packet data conversion protocol. So basically, those are radio-specific protocols that are used mainly for retransmissions on the radio level, and then making sure that at the radio link is reliable in order to send all these IP packets from the mobile to the base station. So once these packets from the mobile reach the base station, then that has to be then encapsulated again on top of IP packets. But then we need to have a different protocol. So basically, as you see, the original packets on the top from the device, they go inside the GPRS tunneling protocol, the GTP. So why do we need that GTP, which then is encapsulated on the UDP and then again on the IP? So the reason is that the mobile networks, the device is moving. And that means that at some point, this connection is changed from one base station to another. So that means that the lower part of the transport protocol, they will be changing IP addresses. So basically now we have the IP address from one base station that connects to another IP address of the serving gateway, the SGB. But then if this device is moved to another base station, then the IP address of that base station is different. So that means that the lower part of the IP packets, they have to be changed. So that's why in order to maintain a bit of transparent IP connection from the device to the public internet, we need to have an extra IP packets on the bottom. And those IP packets are the ones that are changing based on which base station the device is connected each time. So that's why you see that there's an Ethernet, then we have an IP, which is the one that will be changing based on the base station, and then the UDP, user datagram protocol, that it's encapsulating all this mobile-specific tunneling, the GTP, which then inside that will come the original packets from the mobile. So that's the basic how the mobile network takes care of mobility. So basically by building an extra IP packets in between base stations. So then the other thing that we see in the mobile networks is the transport independence. So basically now we have Like in the past, the 1G and 2G and even the 3G was built on circuit switch and then moved into IP. And that means that the transport can be completely transparent. It can be agnostic. So basically, we have all these higher network functions that then can use any transport. So in case you can see that the bottom of this network infrastructure can be like cabling, it can be like Ethernet cables, it can be fiber, it can be even DSL if needed. But then that can be changed and managed separately from the upper part. So basically, that means that we can utilize different type of transport and manage that transport independently of the upper layers. So this is the case that we have all this tunneling. So the IP layers and the GTP tunnel that is changing depending whether mobile is moving from one base station on the other. And then below that, we have different tunnels depending on the application, depending on what kind of functionality, depending on whether we want high quality, low quality. So each device, each user equipment, we have multiple GTP tunnels, multiple radio connections, depending on the applications that are running. So next, now we move into 5G. So as you have seen, all this evolution of the mobile networks has been breaking down into smaller pieces. In 4G, we have separated the signaling from the data. Now in 5G, we have what is called service-based architecture. So that means that, as you can see on the left-hand side, we have few components: the MME, Mobility Management Entity, the Policy Control Function, HSF, which is the database, which was taking care of the signaling. And now on the bottom, we have the user plane, which is the S gateway and P gateway. Now in the 5G, we have even breaking down those pieces into smaller components. Why we do that? I mean, mainly for scalability. And then again, as indicated at the beginning, opening interfaces, creating the possibility of adding new services, new functions that will bring new set of services, new set of applications into the 5G networks. So now the original network functions, they have been exploding to some extent, but then on the other hand, it makes them a bit more reliable, because we have like the same thing that was happening in one big box is now happening in multiple small boxes. It's what is called the microservices. So that means that now we can have, if before we have one MME, now we can have many AMF, which is the authentication and mobility functions, and then we can have many SMF, like session management functions. So basically that means that depending on the service that the device is requesting, it will be managed by one AMF, or it will be managed by another AMF, which will be connected as part of the whole system, but then it might be fully distributed. It can be running in different locations. And then we have also the user plane, which is now the user plane function. Before it was the S gateway and the P gateway. Now we have one component. And then again, this component can be smaller and can be fully distributed. So it can be, we can have tens or hundreds of UPF, depending where do we want to install this UPF. So this is one of the big changes that now, for example, if we have more components, it becomes a bit more like complex in terms of more elements, but then on the other hand is more reliable, smaller functionality. Then it also becomes more distributed. So for example, as I was indicating, that the user plane, the UPF, we can have many of those, and then during the device registration or the attach, then we can identify that, okay, this device requires one UPF that is placed, I don't know, in some data center in AWS, because in the data center we have more services specific for these users. So that means that the UPF that will be allocated for this device will be deployed in some public cloud, AWS, Azure, or whatever. But then it might be that the user wants to have very low latency. So it means that the data cannot go all the way to the cloud and back. So that means that this user will require a UPF which is closer to the base station. So that means that we need to find a new UPF which then can be running beside the base station. And that's what is called as edge computing. So in practice, the edge computing means that instead of assigning one user plane function which is placed somewhere far away on the cloud, then it's selecting a UPF, a user plane function, which is closer to the base station, it's closer to the user. And then all the services and applications will be running in that UPF, which can be just a few meters from the base station instead of several kilometers or thousands of kilometers from the base station. So then we are back in the same paradigm. So basically we are distributing the functionality, we are separating the data from the signaling. That means that we can have more flexibility to manage everything. So we can have full flexibility to manage the transport. And that's one of the new things that, for example, 5G is including. So basically we have a software-defined networking which then can be used together with the 5G to manage the transport. So basically we can say that, okay, I need to have certain specifics or requirements from the transport in terms of priorities, in terms of latency or whatever. Then I can place the UPF closer to the base station, and then with the software-defined network, I can interact with the routers, I can interact with the switches, and then indicate that I want certain actions in order to prioritize some traffic depending on the requirements. So with SDN, what we do is that we set a set of policies, actions into the switches, saying that, for example, if we have a traffic which is from the police, for example, and then we want that traffic that doesn't go together with the other traffic from the normal consumer, then we can set a policy using this software-defined network into the routing that connects the base station to the police dedicated UPF or whatever. And then we can set a policy that can even encrypt that messages instead of using plain transport for normal consumer. So in that sense, we have the possibility that from the 5G, we have distributed network functions, we have a separated data plane, and then we have also the interaction with the transport to make sure that certain traffic from certain users will follow different policies. So in this case, this SDN, we can have several functionality. We can react to some of the flows. So basically, the case of the policy, we can set in advance a bit proactive policies, saying that all the traffic from these devices will be encrypted and will go to this UPF. But then it can also be reactive. So for example, if we see that there's some misbehavior in the traffic, saying, okay, we are being attacked, there's some malware or whatever, then we can also detect that and then react this kind of functionality. So basically the core, the 5G core, can monitor continuously, and then using the SDN can set new policies because it has detected some malware or some traffic that is not legitimate. So in that sense, we can integrate this kind of SDN functionality as part of the packet core, and then altogether then we can build this fully end-to-end system, depending on whether we want to assign different priorities or treat the traffic differently. So where do we need this? Is basically, for example, another aspect of the 5G is that it's not only for consumers, but then the 5G is being also proposed for dedicated industrial networks. So that means that with this SDN and this the different functionality, we can deploy this network in chemical industries or manufacturing or whatever, and then we can set different rules in terms of priority, in terms of different capabilities. And what we do is that, as indicated at the beginning, in Aalto, we were of the first groups that were designing. We were part of this small garage where we were contributing to the first design of the IMS and so on. And then currently we also have a full infrastructure where we continue this kind of research, this kind of sort of analysis of new functionality. And this is because we have the support first from the government. So we have a full operational network with a full license given by the local authorities. We built our own network with a component from Nokia, donated by Nokia, and in some cases from Ericsson. And then we have the full system, which is a real network where we can then experiment and start designing this kind of new services. And this infrastructure is full 5G. So basically, we are contributing to different projects to analyze what are the limitations of the 5G networks, because one of the things that the 5G is promising is this very low latency, high availability, and so on. But then we need to validate, and then we need to experiment whether we can fulfill these requirements. And that's what we do on daily basis using this infrastructure. So we operate the network, we have our own SIM cards, our frequency, and then we can experiment, as I said, with this kind of edge computing, building sort of different deployments of packet core, UPF, depending whether we want to have low latency or different requirements. And then one feature that 5G is defining is network slicing. So with network slicing, it's based on the possibility of this service-based architecture where we have different elements that can be allocated to different services. So network slicing, what we do is we separate a subset of the network at the radio, at the transport. So we use SDN to manage or separate the network, and then on the core. And that means that on top of the same physical infrastructure, we can have multiple networks that can be associated to different group of devices or different services. So in that sense, we can create a slice which consists of a set of resources on the radio. Then with the SDN, we separate a bit of the traffic on the routers on the transport, and then we allocate different UPF or different packet cores. So it's like having many networks on top of a single physical network. And then also one feature for the slicing is SDN and mainly applied for IoT. So basically, we want to have the IoT traffic, which might be quite heavy, separated from the traffic from the consumer. So then it doesn't interfere with the normal traffic. So in that sense, we can create a slice. We separate all this IoT traffic from the normal traffic with their own slice. And then IoT, that's the other sort of new functionality that in 5G is coming. So basically allocating different resources for IoT devices compared to resources that normal consumer data will require. So the IoT require smaller packets compared to higher bandwidth that for streaming or whatever is needed in consumer data. So, and with this, I would like to conclude. So hope I gave you a good understanding of the evolution of the mobile networks, and then what are the main differences and advantages of 5G networks. Thank you.
Thank you, Jose. And if you have any questions, please send them via Zoom chat so we can take couple. We have couple minutes for questions.
Thank you. If you have any other question, this is my email, so you can just send that directly to me if you want.
So there was no questions, and now what's gonna happen? We have a little lunch break, and we'll be back at 1 p.m. with another lecture. And please make sure to do the first quiz. It's open until midnight today. So if you want the 2 credits for the quizzes, it's mandatory for those. So we'll see at 1 p.m. with another lecture. Thank you.
welcome back. Sorry we are a few minutes late. So next up, Antti Toskala will give a closer look about the 5G. She's from Nokia Bell Labs. This is actually pre-record video, so if you have any questions, please send me a chat so we can forward them to Antti and answer for your questions. So hope you like the lecture. See you.
Welcome to the lecture on 5G physical layer. My name is Antti Toskala, coming from Welcome to the lecture on 5G physical layer. My name is Antti Toskala, coming from Nokia Standards and Technology Unit based here in Espoo, Finland. And I will be taking you through this 5G physical layer, what it is all about, and what is also a little bit coming in the future as the next development steps. So first of all, here is this structure of today's lecture. We'll be going through different areas of the physical layer, starting from the key technology components, compare a bit what's difference between 3G and 4G, and then go through these different elements, waveforms, frame structures, channel coding, and so forth. Finalizing with this small talk about what is the current availability in terms of devices, what do they support and what do they don't. And on the picture on the right hand side is then the reference material, so commercial part of the presentation, so the book written by not only myself but many Nokia colleagues, as well as colleagues from some other companies like MediaTek, Skyworks, NTT Docomo, that bring the expertise of 5G together. If you look the 5G radio technology, so what was new compared to the previous generations? So first of all, we had to deal with elements like new spectrum, meaning that we were addressing higher frequency band than previous generations. On one hand, we were also from the day one putting a lot of emphasis on dealing with the beamforming, which of course when you go to higher frequencies, antennas get smaller, then doing this kind of antenna arrays gets more realistic from size and cost point of view. So then the beamforming was now really taking into account from the day one of the radio interface design. Then this slicing flexibility, meaning is that even though we defined this kind of radio with a massive data rate and capacity capabilities, we also took into account that first of all, not every device may not be in the future needing needing these several gigabits of data rates. We also need to be able to be flexible to configure the system in different ways, including to operate in a situation that you don't have that much traffic, that you want to save energy, to be energy efficient, to take these current climate challenges into account. Further, we are now really dealing with the multi-connectivity, meaning that with 5G we enable that we are connected together with the 4G LTE connection as well as 5G connection. This kind of dual connectivity we have practiced in the standards in the earlier generations, but now it's a real first time that it's really taken into use and is the baseline feature of all the devices you may already have in your pocket. If we now look what is then difference to this 3G, 4G from the radio technology point of view. We can see elements like take the waveform. 3G of course was totally different based on code division multiple access CDMA. Now with 4G we already took the OFF-DMA into use and we continue that with 5G, but we of course add a lot of more flexibility, as you later see, in terms of parameterization, where you can apply it low band, mid band, very high frequency band as well. Uplink waveform is another element, CDMA in 3G, single carrier FDMA in the 4G side, and now we have also OFF-DMA, orthogonal frequency division multiple access, together with the single carrier FDMA operation in uplink available. These technologies being suited for a little bit different needs. One suited for cell edge operation when you're power limited, other one suited for multi-stream uplink transmission when you have more link budget available. Channel coding was something that between 3G and 4G we only applied basically copy and paste, nothing major changes. But now with the 5G, with the increase of data rates, challenges with the power consumption in the handset as well, we had to take something more efficient. So we took the LDPC, low density parity check codes into use. Technology known from, be that from these space missions, be that from Wi-Fi, but we did improve it, make it more flexible, more advanced compared to these previous generations of low density parity check coding. Beamforming, 3G did not really consider that in reality, 4G only partly, but now we have full support starting from the initial access as we discuss shortly. And from the spectrum point of view, previous generations were typically limited to 3G up to this 2 GHz range. 4G went up to this 6 GHz if we take the unlicensed into account. But now with the 5G, in the first phase we have done the support around the 50 GHz range, now working even higher, and we'll soon enable up to 71 GHz. So clearly a larger range of spectrum could be utilized. And that naturally is linked to this bandwidth we have up to 200 or even 400 MHz bandwidths in the millimeter wave supported by the devices. And so additionally, we enable more energy efficient network operations, so really green networks. We are lower latency, faster decoding, shorter TTIs, transmission time intervals, as we see shortly. And many solutions that we developed in LTE standards did not necessarily implement, but now they are really rolled in the field in practice with 5G. So let's have a look in some of those interesting ones in more details. For spectrum point of view, indeed, even if I say now that we are up to 50 GHz, 71 GHz short, of course in the first phase you need to build coverage, and that's why the low frequency bands come to the play. We have those frequency bands like 3.5 gigahertz, as discussed shortly, is really the major band, also here in Finland and in Europe in general, but also being rolled out in US and Asia quite widely. And then this high frequency band then offer future capacity expansion. So if you take the 3.5 gigahertz band range as an example first, so there typically an operator has around 100 megahertz bandwidth. And that's something what all these first phase devices support. Every 5G device in the market today, if they support this 3.5 gigahertz frequency range, they support 100 megahertz bandwidth, which is clearly 5 times more than the basic LTE bandwidth. And that of course has a clear direct linkage to this data rates you are supporting. There are of course several existing LTE bands that have been specified as 5G bands. So over the years we will see refarming when operators will move more and more of their spectrum assets to be operated using 5G technology. This millimeter wave bands 28 gigahertz range in Europe, you talk more maybe 26 gigahertz range, was not used earlier by the mobile communications, and now it's been rolled out, but still slowly. It's mainly in US. In Europe you don't see much of that, if any. Like if you go and buy the latest iPhone in Europe, the versions don't support the millimeter wave. If you buy a version in US, they do. So that's also a clear indication that in the other markets those millimeter waves will come still later. So to be able to deal with these different sets of frequency band, you need a lot of flexibility in the system. And to enable that, we defined many different subcarrier spacings and are defining even more in the standards for later releases. And that was that for the low frequency bands, using the same as LTE, 15 kilohertz works well. But then you have, if you want to support larger bandwidths, then the amount of subcarriers you would need would tend to be quite large. And from the fundamentals of OFDMA technology, having very large FFT sizes would not be ideal. So when you go to this 100 megahertz bandwidth range, you want to use larger subcarrier spacing so that you don't need such a huge number of those subcarriers. Same time with OFDMA, when we increase the subcarrier spacing, our simple duration in time gets clearly shorter. So that means that we go down in latency as well, meaning that how long does it take to transmit, for example, the typical 14 symbols. With the 15 kilohertz subcarrier spacing, it takes 1 millisecond. When we go to 30 kilohertz subcarrier spacing, it takes only half a millisecond. And if we go all the way to this 120 kilohertz subcarrier spacing, which is intended to the millimeter wave frequencies, it takes only 1/8 of a millisecond to transmit. That, together with faster processing times, is a key for enabling this kind of shorter round trip times in 5G compared to the previous generations. Then when we go to this millimeter wave, indeed, another issue comes that this phase noise becomes an issue, so that your frequency estimation is not necessarily so accurate anymore with the higher frequencies. That's why also the subcarrier spacing needs to be higher, so you are able to cooperate, deal with that, and you don't get too much interference between the subcarriers. That would be the case that if you try to operate 15 kilohertz subcarrier spacing on this 26 gigahertz frequency, for example. So then let's look the waveforms next as a next item. So in release 16, indeed we have the OFDMA in both directions. In uplink we have the single carrier option for the cell edge cases if we are limited with the power operation. The motivation for OFDMA, both in uplink and downlink, was to be able to have a similar solution dealing with the interference handling. Think about side link communication. Side link communication is the communication between the handsets. And OFDMA then allows this kind of efficient multiplexing of different services in frequency domain, which is then needed as part of the 5G operations. Release 17 is addressing even further higher subcarrier spacing values, as we are addressing especially the 60 to 71 GHz frequency bands. That is mostly going to be unlicensed use, but in some regions also licensed operation on that band. But that clearly building for the future, something that could expect to appear in the market maybe end of 23, early 2024 timeframe. And currently the discussion in 3GPP is that we don't likely go above 71 GHz, as there are not new frequency bands now identified available for the 5G there, but some studies may be started to look for new waveforms. OFDMA with the very high frequencies is not necessarily going to be so attractive, so it may be more towards this kind of single carrier waveform type of considerations for very high frequencies when you go towards the above 100 GHz and beyond. So now if you look at the frame structure of 5G, compared what is the difference to LTE. First of all, similar to LTE, we support both FDD and TDD, frequency division duplex and time division duplex operations. Recall, with FDD you had to separate part of the spectrum for uplink, separate for downlink, but with TDD we were sharing them in time domain. Now with this reference signal structure, with LTE, the reference signals are, so to say, all over the place when you look at the slide. That is to allow this kind of good interpolation to create this channel estimate both in frequency and time domain. This is nice, but it has one major drawback, is that you need to receive the whole frame before you are able to create your channel estimation. And that's only when you can start decoding your data. And that costs you in time. You introduce delay. With with 5G, the idea is that you have first your control signaling, then you have your reference data that allows you to build a channel estimate, and then you are able to do the data decoding straight from the beginning, which means that ideally you are done with your decoding almost when your data stops coming. This has some drawbacks naturally for an environment where you move a lot, so that then the channel is changing too much, and in those cases we do need to add additional reference signals to the end. And that's why later when I show something processing times, you see two values as this extra demodulation reference signal. If that is in use, then of course device need to capture that one before you can do the real full channel estimate and start decoding your data. Channel coding was perhaps the most controversial element of first 5G design choices we had to do in 3GPP. One thing was that also engineers dealing with this had been used with turbo coding since early days of 3G, and that had been specified in 1999. And now we were dealing with this, we had adopted the same solution basically for LTE as well, and now was kind of a big decision to change the situation and take something else into use when everybody had been used to that turbo coding is what we are using. The problem with turbo coding was the fact that devices with very high data rates would become really too hot in practice. And I don't mean the hot in design, but from the temperature point of view. So we had to really have a cooler devices so that the channel coding solution could not use so much energy, because that was the problem with turbo codes going up in the data rates. More and more energy is consumed in decoding the data. That's why we were evaluating these different alternatives, and we had also some other choices like polar coding into consideration. Was fairly new, but it did not offer anything, any real improvements over low density parity check codes, which were clearly superior in their energy efficiency and provided really good area efficiency as well, that your chip surface area is not too massive to make the decoder. So then low density parity check codes were chosen as the channel coding solution with 5G. For the layer 1 control signaling, we do some other solutions, sometimes repetition, sometimes Riedmüller, or sometimes this polar coding. But for real device performance, of course, it's the actual channel coding that makes a difference. Low latency comes from multiple elements. One thing indeed is what I have described, that you are really able to send data quickly, so that it doesn't take too long for data to travel over the radio interface. But other element is that once the device receives the data, how long you need to process that before you can pass it on towards the upper layers and eventually for the application you are using. And now, with the solution described earlier, the decoding can be now clearly faster, like you can see in the picture in this easy case, in the sense that you have FDD, meaning uplink is all the time available. Already during the next transmission time interval, you get the feedback for the uplink whether your data was received correctly or not. And if it was received correctly, then of course device can push it on towards the next layers in the protocol stack. If you compare with LTE, LTE was only done with the decoding some same time as with 5G, we would already have a retransmission available. So that shows a clear difference between LTE and 5G in this latency performance, in the speed of decoding, as well as how fast you get the stuff over the air interface. Besides this 14 symbol, we have also other means to make it even faster. So we have this concept called mini slot, which means that you don't have to allocate full 14 symbols. You can allocate 7, 4, or 2 symbols, those called mini slot. And that again cuts time from the operations and can make the latency even smaller. Where would you need such a extreme latency? It doesn't matter if you're watching Netflix, but for this kind of applications in the industrial environment, for example, controlling the robots, machinery, this ultra reliable low latency communication, that is the field where it really makes a difference. Is the air interface delay? Are you dealing with 5 milliseconds, 10 milliseconds, maybe 15 milliseconds that we get typical when we test LTE as of today? But now we can go to this kind of 1 millisecond level, or even smaller than that for best cases. There are more future-oriented structures in the specifications. One may, if you read the specifications or the book, you know these concepts like self-contained subframe, where also the uplink feedback would be encapsulated, already provided during the same frame where the downlink data came. Those are of course more for the future looking, not supported in the devices as of today in the marketplace, but may come to the play in the future as also processing technology gets all the time faster and faster. So now if we move a bit for the next section of the story, meaning the beamforming. So what have we done in 5G differently to earlier generations? So first, as I mentioned, when the higher frequency we go, already 3.5 gigahertz, the antennas get smaller, you can afford to include more antennas in the devices. And not to mention the millimeter waves, then the antennas are really small, and you can expect the devices have even the multiple set of antennas in them. Beamforming allows to boost the capacity. As you can imagine, that instead of having just one sector covering, for example, this building from the outside base station, you can have inside the sector different beams that have some isolation among themselves and really focus the transmission for that particular user or group of users needing data at given time. And that is the way like dividing this basically, like if you think about sector, something similar in that similarity. If you would think the idea that we go from 3-sector cell to 6-sector cells, we are splitting these kind of smaller pieces, the resources in space and frequency domain. Also, with the beamforming, then when instead of not sending for the same sector or full sector, meaning indeed we focus the energy, we send the same amount of energy, but focus in a narrower direction, not over 120 degrees, but maybe 10, 20 degrees, if you think about this 360 site. And that allows, of course, us have a better link budget and compensate a loss that we get with the higher frequencies. As you recall, the higher frequency band, the higher is the attenuation you get for your link budget. To deal with this beamforming operation, we typically apply this kind of hybrid beamforming, especially with the high frequency bands. So that means that the base station can only transmit at one direction at a time. So one beam can be active at a time. And that means that we need this kind of special measures also to be able to figure out which beam is the best one for a different particle device. And that's what we have, this what we call the beam sweeping, which means that we are transmitting one beam direction at a time, and device will measure, is it beam 0, is it beam 4, is it beam 5, what is the beam that I receive the best, simply meaning what is the strongest for me, and give that feedback for the network, and network then can use that beam for the device in the next transmissions. And that allows that we have this kind of continuous tracking when devices move around in the area that is served by multiple beams. Devices themselves can have directivity as well in the millimeter wave, but that's more detailed discussion on that one. On this kind of MIMO technology, multiple input, multiple output, we have a lot of different alternatives. If going into the deep details, it would be maybe a lecture of its own on the MIMO, but we can operate. This operation is often based on this CSI ARAS, so channel state information reference signals that the devices measure and give feedback for the network so that the network can configure the best possible beamforming transmission. We can have one of those, or we can have multiple those, depending what kind of beamforming array we have available in the base station side. And then the device measures, is told what is in use, measures all of those, and then provides feedback, suggestions that, okay, what kind of transmission would be good for me in a given point in time. For TDD bands, other element to use is this channel reciprocity, which means that because now we are using the same spectrum and same piece of spectrum for both terminal transmission and reception, which means that the signal then typically propagates, of course, roughly the same route for both for transmission and reception when we are talking about same part of the spectrum. And that's why there the possibilities is also used things like sounding reference signals. Device can also send this kind of known data for the network, and a network can measure that, and based on that figure out what kind of beamforming to use to reach such particle device. Sounding reference signals, that's what they are used for. When you go to this millimeter waves, again we have a lot of different implementation choices. One may do this kind of single panel array that is basically able to, with this polarization, maybe able to deal with these transmit drivers to create 2 different MIMO streams, but only one device at a time. We can do this kind of multi-panel array situation that can serve maybe one device with basically multiple beams or more MIMO streams, but typically the devices don't do many MIMO streams on the millimeter wave because it's not so beneficial. But more advantage solution is actually then when you have multiple panels to use it as a multi-user MIMO, that you try to seek this kind of devices like pairs or more than one device, that maybe they are a little bit in the other end of the area you are serving, and simultaneously you send one beam towards the other device, other beam towards the other device, and serve them simultaneously, and that way increase the sector peak throughput, but not of course the individual device peak throughput, but you are able to serve more devices in a given point in time. And then for that one you have indeed the same solutions. You can have this channel state information, you can use the sounding reference signals, but typically the higher frequencies you go, then more beams you can enable, also from the implementation point of view as well as from the standards point of view. The low frequency bands typically support only 4 or 8 beams to be used, while higher frequency bands can go up to 64 beams or even higher in the practical implementations, as well as from the specification support. For the layer 1 channel structures, basically we have this set of channels in use. We have uplink shared channel, we have downlink shared channel, terms known from the LT side as well. Physical broadcast channel is to send the necessary broadcast information. There's a downlink control channel, physical downlink control channel, PDCCH. Same way uplink direction, we have physical uplink control channel, PUCCH, and then the PRADS random access channel for contacting the network in the first place before you have a connection up and running. And then we have physical signals, many of them known from the LT side. Some of them are new, like these phase tracking reference signals needed for the millimeter wave operation. Otherwise pretty familiar from the earlier technology. Reference signals for channel estimation, or channel state information reference signals for measuring the channel and providing feedback for the network. And then this PSS and SSS are the primary and secondary synchronization signals. Those are the ones you use to find the cells in the first place. For the synchronization and broadcast operation, we have this thing called SS block, and that is the one that the devices will seek first. So this is used by devices to identify what is the cell. So they find that from this primary and secondary synchronization signals. They get these things called physical cell ID, identify the cell, and then this broadcast channel gives the necessary parameters to access the network. And for example, where do I find the random access channel and other network parameters. And this sync block is indeed, when we have this earlier, what I showed, the beam sweep, is the sync block. This is what we send periodically to each of the beams this is what the devices measure based on this one, what they find the network in the first place. For downlink channels, physical downlink control channel, PDCCH, this is in the first part of the frame in downlink direction. So first comes control information, then comes the reference data, and then comes the actual PDCSCH symbol, so physical downlink shared channel. And we have a different formats for physical downlink shared channel, simply to use basically as a link adaptation. If we have device next door to the base station, we don't need a lot of channel coding because we have a very strong signal in that case. On the other hand, if a device at the cell edge, then we want to protect the signaling well because and use a lot of redundancy for the channel coding. As like every system, if you lose the control signaling, that tells you what you are supposed to receive in the first place, then of course it doesn't matter how well we send the data itself because the device will not know it's coming. So that tells indeed whether there's data coming for a particular device and where in the, for example, 100 MHz carrier this data is located. Physical downlink shared channel then comes after. Now I also have shown here the example of this demodulation reference signals that come after the control channel, and then rest of the symbols is used for this PDSCH unless we would have this additional demodulation reference signal in place. We have 4 different modulation sizes, so we have the QPSK 16 COM, 64 COM, and 256 COM. And now in release 17 we are adding for downlink also this 1024 COM modulation, mainly beneficial for this kind of fixed wireless type of access operation when you have a really good signal conditions. Specific thing shown here in blue color, you see this continuous line. So that is this phase tracking reference signals that would be in place to allow the device to deal with this phase noise, to have this kind of known signal there in the millimeter wave operations. Clearly, on this kind of slower frequency bands, smaller than 6, or maybe based on the release 16, I could say below 7 GHz, you don't need this naturally, as you don't have such a problem with the phase noise. On the uplink direction, we have this uplink PUSCH, physical uplink shared channel. So first of all, the uplink transmissions, with the exception of the control channel, but for data, is always based that we get the permission from the base station when we can transmit in time domain and where in frequency domain. This allocation could be something that could be like repetitive allocation sometimes, but quite often it's dynamic to really not book the resources just in case, and that comes on the downlink control channel as well. And then in uplink direction we can have also the single carrier transmission besides the off DMA in place. On the modulation sides, it's the same set of modulations, but for this low peak to average ratio case, when you are at the cell edge, we also have this pi over 2 PPSK in place. And then the device will then send this UE specific demodulation reference signal so that the base station on the other hand can decode the data. Physical uplink control channel is something that carries uplink control information. If you are sending uplink data, then of course you multiplex this together with the uplink data transmission, but you need to be also able to send uplink control information when you don't have uplink allocation. So then you can of course send only control information, where the key message is that things like, okay, my previous packet failed or did not fail, and or other way around that now I have data in my buffer, so to have this kind of request to get resources allocated. Further in uplink channels, so we have this PRACH, physical random access channel, and here the beamforming comes to the play. So now that beamforming is there from the day one, so that means that devices need to figure out not only from the broadcast channel that what is the resource to use for the random access, but also the devices do need to measure what is the best beam I should use. So now actually I need to select such a random access resource that is occurring in the beam that I measure that is best for me. And all this kind of that kind of information you get from the broadcast channel transmission. That what are the resources, and then I figure out, for example, in here that if this beam number 5 is the best for me, then I select such a random access resource that I know that when I send it, the base station is listening the beam direction number 5, because otherwise, of course, my random access resource will be wasted. But all that, when it has been taken into account from the day one, allows then to fully benefit from the beamforming, including when I'm accessing the network. It allows me, the network, to then direct the beam to the direction that I am, and then I get this maximum link budget also from a random access operation. Because otherwise, if the random access would be then this omnidirectional channel, but then otherwise I would be using beamforming, and then it could be a situation that the data connection could be maintained, but I don't reach the network because my beamforming doesn't support random access operation. But that's why it was important that beamforming was there from the day one, part of the design, as these kind of things are often difficult, if not even impossible, to add afterwards for the system. So now here also you have the term beam association visible, which means basically that in downlink, if I receive the beam number 5 being the best, then indeed in uplink I should understand that that this is what I use in the random access. And then ideally also when you think about the millimeter wave, if there's some directivity in the handset, it should understand that if the particle direction where my best beam is coming, if I have any directivity, I should also direct my transmission to the same direction and not somewhere totally different. So that's the meaning of the beam association in that sense. So what are then the first phase devices all about? So basically the first phase devices that came to the market 2019, they were supporting already, which was the first mode of 5G operation, this kind of dual connectivity. That was referred like non-standalone 5G, that you first had to access LTE, and then when there's enough stuff to transmit, then the 5G was activated on the side. The current set of devices, including the example devices on the slide and what I'm having here, this is like a Nokia 8.3 5G. So they do support the standalone 5G operation, which means that networks that are now moving to this, that you can directly access 5G. You don't have to first go via LTE, or you don't need to have LTE on the connection active. That will allow also smaller latencies. You get all the 5G benefits, faster connection setup when you don't have to go through LTE. And then when you do a test, you don't get only higher data rates, but indeed the part of the packets then does not go through via LTE channels. Then that allows that the latency overall is smaller. and we can get already in the market pretty high data rates. So this example number taken back home in my place outside, of course, then I get this nearly 900 megabits, but still also inside I get, depending which room, 600 to 700 megabits data rates, which is quite impressive. But I happen to live relatively close to one of the base stations by one of the operators, and the devices indeed, they all support this in the European market. They typically indeed don't use the millimeter wave, but they support this 3.5 gigahertz band, often referred as a C-band, that supports 100 megahertz carrier. It's a mandatory for device to support this 100 megahertz. It's mandatory for device to have 4 receiver antennas. So that gives this kind of device capability in the order of 2 gigabits as a peak data rate. That could be achievable basically, that if I was the only user for that base station and very close to the base station, I cannot get that kind of data rates myself for a given reason, that of course my subscription has some limits that will not give me 2 gigabits. So then there's no point for me going even closer to the base station, as then my subscription will start limiting this. But at least in my case, I can see that I'll get quite impressive speeds, and I'm going to ditch my ADSL connection that gives me 10 times less in very near term in the future, as soon as I get rid of my existing DSL contract. And in the US market, indeed, the devices support this millimeter wave operation with 2 receiver antennas. You don't get, even the antennas are very small, you don't get that much diversity in the channel you get with this 28 gigahertz, because propagation is such that if the signal reflects somewhere far, it gets already then so much attenuation. So that's why it's a 2-stream MIMO only for the millimeter waves. But of course the bandwidths are larger. Devices support 400 or up to 800 megahertz of bandwidth, and there you can get this kind of in the order of 4 to 5 gigabits data rates possible with that kind of deployments. But in most markets, the millimeter wave is still coming, and also on the standard side, we are still doing a lot of improvements to make the millimeter wave operation even more efficient and more reliable. But with the millimeter wave, of course, it will be more for the hotspot, more local, as the coverage on the millimeter wave is going to be limited. And like in this kind of campus, you would really need indoor base stations from the outside. It doesn't really come through the walls in practice well. And so this is then still basically the summary, what I have described. So we have a high performance radio in place, also supporting the millimeter wave, but those come later, especially the European market. And all devices support the dual connectivity now, later the standalone 5G operation. And we enable really high data rates, low latency with this, and we expect many different uses in the industrial case in the future. Then final remark is that if you think 5G is your thing, you are eager to learn, not only here in Aalto University, but in the future a part of your career. Also from our side, we are continuously hiring people for Nokia, getting new talents to work on this exciting developing of 5G. So please follow our offering. Here are a couple of examples available as of today. Thank you very much.
Okay, good afternoon, everyone. Really great to see you here. We are now about to start. My name is Sasu Tarkoma, Professor of Computer Science at the University of Helsinki, and also the head of the Computer Science Department. And today I will cover AI and 5G, especially focusing on deployment aspects. So that's the topic for today. And as we know, AI is now a very hot topic, and we have more and more applications running over 4G and 5G networks, having AI elements. So it makes sense to study what 5G can do for AI, but also we need to study that what AI can do for the network itself. So these are the interesting directions here, and I will explore these in my lecture. So now to get going, so today I will give you a brief introduction to the 5G architecture, and I will focus on edge computing, and then how AI relates to edge computing and the paradigm we call edge intelligence, which is really in a way the combination of edge computing and AI methods for supporting the network and for supporting the applications. And then I will briefly discuss recent work in the 6G area. So of course we have now 5G, but then after 5G there will be 6G, and we are already now looking at what things will be important in 6G. So I will talk a bit about the 6G white paper on edge intelligence and how some of these components, some of these notions might then be part of the forthcoming 6G architecture. And then I will focus more on the examples related to deployment of AI and of sensing through 5G and beyond systems. And I have a number of cases that I will cover. And these cases are motivated by our current research in this area. So I will focus on how AI can help us engineer and deploy better networks. So we call this network and slice generation. I will talk about network security, so how we can deploy AI into the network that would then make the network safer, would protect us from different attacks. And then I will also focus on AI for sensing, for environmental sensing, and also for sensing in industrial settings as well. And then we have a brief conclusion for the topic. So these are the topics for today. And now to start with 5G architecture. So of course 5G is part of the continuum, so that we have 4G and 4G having very good properties for mobile broadband, but then for some other cases, verticals like massive machine type communications for IoT and for ultra reliable communications, 4G is very limited. So we have certain requirements that our applications today have that are not met by 4G, and 5G was intended to address many of these emerging requirements. And the three key areas are now presented by this diagram. So we have enhanced mobile broadband, we have the machine type communications, and then we have ultra reliable and low latency communications. And these address a bit differing concerns. And the takeaway is that we have different applications having different requirements, and the network should accommodate these requirements. So we should have flexibility in the network programmability that would then enable us to accommodate these different requirements. And for 5G, we have these three key domains, and these also correspond to three network slices. So network configurations, then having good support for the use case. And now looking beyond, so of course we have also combinations of requirements across these three areas and so on. So the world is not done yet. So we believe that in 6G we will have even better possibilities of taking application requirements into account when we configure, tune the network for the applications. So that's the direction we are heading at the moment. And we know, of course, that the application requirements are very heterogeneous. Here you see a diagram illustrating the delay and the throughput requirements, expectations of well-known application areas. And you can see that we have really, a lot of different requirements by the applications. So there is no one size fits all for the applications. And we have some of these more straightforward applications like monitoring networks, sensor networks, in which we have a very kind of good tolerance for delay, and we do not require a high throughput. And then we have applications like tactile internet, where we have really high demand, so very low latency and high throughput is required. And now our network should be able to accommodate these different cases. And thus we kind of can approach this from the challenges point of view. So looking at the different use cases, applications, so what are really the problem points, what are challenges there? And in many application areas, so we do have the requirement for local computing power, that we do something that's very intensive, and we need to do most of the computing locally or within the region to keep the low latency requirement. So that's one observation that we can make, and certainly low latency is something that is needed for many use cases. And of course, for some current and many emerging applications, so we have also increasing bandwidth requirements as well, like for example, AR and VR applications and so on. Of course, we have 8K videos and such for the mobile broadband side as well. So we see these as crucial challenges. And then we have privacy aspect as well, that we do data gathering, and we need to, of course, ensure data ownership. We need to ensure data privacy. And we can ask that what can the network do here for the applications? And for many of these, we see that we can support the applications by having computing near the devices, near the handsets, near the sensors, and this is edge computing. We bring in computing capabilities, these other resources at the edge of the network, and open up those resources for the applications so that we can do distributed computing that can take locality into account. That's really the essence of edge computing. And we see this as a kind of interesting element that is now being deployed over 5G, and is part of 5G, and will, I believe, certainly be part of 6G as well. So edge computing has a role to play here, and how to support applications, and also how to support the network as well. So now just summarizing some key aspects of 5G, that what is happening with 5G and the different kind of iterations of 5G. So of course we have the radio access network part, and there we have better radios, we have new spectrum for 5G, and many innovations that help to improve the data communications. And we have also cloud, so virtualization is having an effect here, that we can do baseband processing in the cloud, and also at the edge of the network, and that's in a way paradigm shift for many things, that to have the cloud support our activities and support the base stations. And then for the core network, so for the more fixed network part and the cloud part, so we have a service-based architecture, and we have the network slices. so better support for programming the underlying network and its capabilities to meet the requirements of the applications. And we have 3 slices and of course going beyond 3 slices as well. And then we have this edge computing capability for supporting the applications with this nearby computing, the capabilities that what we have through the network. So this is what we are now having in 5G. And of course, there are still many iterations to be done in 5G to get most from these developments. And then we have the 6G coming up to kind of continue this evolution of the cellular architecture. And now to provide some details on this network slicing. So of course you may have heard about this already. So and I already gave a very short definition of the network slice. So so it's really about this programmability of the network, being able to have the network slice that consists of the RAN part and then the core network part, having these network functions placed over the slice. And the network functions, they relate to the network itself, and then also to added functionality that the network is able to offer. And this needs to be provisioned and managed, and through this we get better utilization of the hardware resources, and can also better then accommodate the application requirements. And the network slices are now being piloted in a way. So we have 3 slices, and my expectation is that in the future we would have more than three slices. But this is part of the evolution of the network. And then we have something like this, that we have the slices, we have the different network and also application capabilities then distributed over the slices and over the edge servers. And what is really interesting here is that how we then deploy sensing and AI capabilities. So application-specific sensing and AI capabilities over the network slices. And this is something that we have been investigating quite a lot in recent years, that how to do this for different use cases, and how to generate these slices, how to generate the configurations, and place these functionalities over the network. And this is, of course, something that is forward-looking, but already in today's networks, we have some of these characteristics in place. There is a lot of optimization being done in how the network slices are kind of maintained. But from the research point of view, this especially the sensing and AI capabilities, so that's still an emerging direction, and there are many interesting questions still that need to be addressed. And as a kind of key takeaway, so programmability is now the key here, that we're able to program the network slices, we're able to program the deployment of the sensing and AI capabilities, do the optimization of this, do it offline, do it online, and this then would ensure that we are able to kind of optimize resource utilization and then meet the requirements of the applications. And what is very interesting here is O-RAN, which is a set of open specifications for opening the radio access network. So O-RAN is really aiming to open the RAN and have cloud native interfaces for then connecting these RAN related components and enable to program these. And this is very interesting because this enables component reuse, it enables flexibility in RAN design. It also supports innovation. And especially from the academic point of view, so it's very kind of difficult sometimes to do very hardware-oriented RAN access network research. So O-RAN would help there as well in terms of supporting researchers, and would help also pave way from the lab work to an actual product as well, so speed up the innovation cycle. So O-RAN is very interesting, and what is also interesting here is the radio intelligent controller that's specified by the O-RAN activity. And this radio controller would then help us to configure AI tasks and activities for the RAN domain. So of course we have controllers now for the core network side, but it's been an open issue that how to do this this in a way standard-based and interoperable RAN control, and the RIC controller here is a step towards that direction. And this is an evolving set of specifications, an evolving initiative, and of course we stay tuned for updates here. But it's very interesting from this kind of innovation point of view, and would help in exploring new designs for how to have AI in the radio access network. And now we go forward to edge intelligence, and we see that we now have the slices, we have the edge computing, we have the radio access network and the RIC controller. So edge intelligence now kind of comes into the picture and helps us to kind of coordinate these to then get to this more optimal situation for the application, and take these different concerns we have been now looking at, like latency and processing power and privacy and so on into account. So edge intelligence really, it's about being able to offer these basic resource-related services like data collection, caching, data processing, data analysis in the local environment. So being close by to the devices which then produce and consume data and the results that we then produce. And of course, we gain the latency benefit and we gain the privacy benefit by doing this. And we have two directions here. So we have AI for edge, which is really about having AI help in doing radio management with the RIC, with the, for example, the cloud RAN, helping with network management, helping with network slicing, doing function placement, and so on, supporting also the applications. So, so AI has many things to give for the edge and for the network, but then we do have also the edge for AI view, in which edge servers, edge computing helps AI applications. And here we have the distributed and decentralized paradigm for applications, that how do we learn in a distributed environment and utilize edge servers for learning, for inference, and so on. And in recent years, we have had really many kind of foundational contributions in this area. For example, we have federated learning, we have transfer learning. So we have these building blocks that we can use to then create these distributed AI solutions. And edge, of course, it provides also the programmability point of view. So the applications can be then connected through the edge to the information we have about the network, about the user devices, about base stations. So we can do, for example, quality of experience monitoring and optimization through edge servers. So in a way, connecting the application view and concerns with the network view and the network concerns. So we can bridge these two worlds through edge computing. And then certainly we have the privacy and ethical data management as things we can then do at the edge of the network. So to kind of summarize the current direction, so we go from the left-hand side here, which is the centralized cloud-based AI that we frequently today employ, to the right-hand side, in which we have this distributed and decentralized AI being used, so that the AI, the model creation, so learning and also inference, they are highly distributed over the environment. So over the network elements, over different clouds, all the way to the end devices and sensors. And this is a very kind of interesting and highly likely future direction in which we are now progressing. And we are also having some of these foundational ingredients to build this infrastructure. For example, federated learning is one example here. Edge computing is, of course, a key ingredient. And so we are now, in a way, realizing this distributed computing vision that I believe is not very new. So I believe we have had this vision for many years in computer science, for example. But now we are kind of progressing towards this vision, and 5G and then 6G are very important steps here in how to distribute this processing and make the network more efficient. So that's the trend that we have at the moment. And we have been now studying edge intelligence. It's many forms, many phases, through doing literature study, and of course by developing methods and studying the methods. And through the study we have now conducted, we have identified 4 key sub-areas in edge intelligence. So we have identified edge caching relating to data management. We have identified edge training, so building the models, learning. We have identified edge inference, so using the models, doing predictions with the models, and then edge offloading, which is about using the different resources we have in the environment to offload these different, for example, learning and inference processes, tasks over the environment in different, with different strategies. So 4 key sub-areas having certain more elementary building blocks and of course parameters and so on. And as a takeaway, so we can conclude that we have a fair amount of work done in this area. We have some good baseline solutions, but of course there is still quite some work to be done here in using what is already established, and then addressing also new concerns, new features that are needed. And this is of course something that the scientific community is very active on at the moment. So we have really high level of activity in the international communities working around edge intelligence. So just going through these different sub areas. So the caching aspect, of course, is very important, that we want to ensure the reuse of data and ensure that data is available when needed. And these are, of course, the key things that where caching can help. And we can do the caching on multiple levels. So at the devices, we can do it at the base stations, such at edge servers, in the telecom cloud, and of course in some more far away cloud systems as well. And especially interesting is the caching at the edge of the network and in the base stations, how to kind of support that. And for content, of course, caching is everyday activity. So we have established practices how to do caching for content, but for the AI kind of aspect, so there we still have work to do, how to cache the models and do model updates and basically streamline the processes that how we operate with machine learning models in the distributed environment. So data management is still a partially unsolved challenge when it comes to distributed decentralized AI. So there's work to be done there. Then we have the model building, so the training part, which is really very interesting. It's of course very demanding. So building models is not easy and it takes a lot of resources. So optimization and use of accelerator components is really fundamental here. And this is where we see a lot of interest at the moment, that how do we create machine learning models in the decentralized distributed environment, in what use cases we actually need to do this, where we benefit from this, and how we use the available hardware resources in an optimal manner, for example, accelerators and such. And there, I believe that there is much work still to be done here in terms of orchestrating the distributed, decentralized learning processes over the environment. So orchestration is the term that is frequently used, how to kind of achieve this innovative deployment capability that we are at runtime able to have these learning tasks, inference tasks distributed and configured over the environment for meeting the goals. And orchestration is a very exciting area at the moment. So we need orchestration for 5G, and certainly we will need new solutions for 6G as well. And optimization in its many forms is really fundamental here. As baseline solutions, I've already mentioned federated learning, and then we have transfer learning for then adapting the models to new use cases. And that's also a very interesting direction, that how can we really reuse the models that we then create, for example, in IoT and in the industrial setting and so on. And that's something that is now attracting a lot of interest in the research communities. So then we have inference, so using the models, making predictions. And in many ways, this is more straightforward than building the models. So in a typical case, it doesn't require that much hardware resourcing, but of course may require to some extent, so that we have the accelerators that we need to utilize, and also various compression techniques for managing with resource constraints. So we may have a very big model, so how do we work with the limited resources available at the edge of the network, for example, or on IoT devices. So I would mention also resource constrained operation as something that for which we have already solutions like compression solutions, but we still have many open questions in this area, that how can we do more from the theoretical point of view and also from the practical point of view as well. And then we have the offloading, so that we use the hardware resources. We are able to send the tasks to different hardware resources for completion. And this relates also to the orchestration I mentioned. And it's a central part of the system, of course, that how to do this. So now looking at the activity levels, given the published works in recent years. So we have been studying this, and the summary, so the takeaway from this analysis is that we have more and more interest in the edge intelligence area altogether. So you see that there is this linear growth in terms of the number of publications published in the area. And we have different subtopics here. So we have the caching, and for the caching, you can see that we have this downward trend. So perhaps we can, as a takeaway, say that caching doesn't seem to be as trendy and as popular as some other topics within this framing of edge intelligence. So we have edge training, gaining some ground, then offloading, gaining as well, and then inference is really becoming more popular. So due to federated learning and other techniques as well. So you could say that this distributed decentralized learning is really booming at the moment. So there is really a very high level of interest to these topics. And now, so just to mention the 6G direction. So going forward in the presentation. So 6G really builds on what I've been now discussing so far in terms of edge intelligence. So we have the distributed and decentralized learning capability. We do inferences, and we do this over the cloud and the programmable network infrastructure. And we then through the 6G activity, so we have the 6G flagship at Oulu. So through that activity, we set out to prepare a white paper on edge intelligence, so the 6G white paper. And you can find this online, and it provides views that how we go from 5G to 6G in this topical area, and identifies also key challenges that are still very much open challenges and would require further work for then getting those forward and then as possible solutions to 6G architecture and 6G systems. And we have two parts here. We have AI for edge and then AI on edge. So reflecting the two directions we have been discussing, and a number of then more specific challenges and points within these. And also overall, we see that there are different levels of distribution that we have here in edge intelligence. So we have the extremes. So at the top, we have the extreme that we have everything in the centralized cloud. And at the bottom, we have the other extreme, that everything is running on an IoT device or the other device. And then we have these more intermediate levels in which we have these different learning and inference tasks at the cloud or at the edge or at the device. So it makes sense to study these different combinations, how to do the distribution. And here one important consideration is that how much training we can do on the cloud and then on the edge. So that's a clearly a very kind of big requirement if you want to do training, so model building at the edge and on the devices. So that will require quite a lot of computing resources. So we have to understand, of course, these aspects when we then develop the orchestration, when we develop the methods, that how to really get to this more decentralized, distributed world. So the cloud white paper provides insights to these, and as a takeaway from this, so the key point is this having the different kind of levels, different layers of distribution affecting the learning and inference tasks, how those are placed over the network. And it's really the orchestration that then manages this. So now going beyond the current discussion, so we go more for the concrete examples. So we will now look at the network and slice generation, and then the security, and then the sensing examples I mentioned already. So we will now go into these. And to start, so we have the network refactoring as a kind of method that we have been working on for many years to understand that how could we kind of repackage kind of refactor networks to accommodate application requirements. And of course, the vision here is that we would be able to take the specification that what the application requires, and then we would be able to reconfigure the network and generate the network that then meets these requirements and has the slice properties and the functions placed and the orchestration mechanism then supporting this activity. And we have been now working on a methodology to kind of try to achieve this. So we have certain steps here for the methodology. So we have first this modularization part, that we kind of take the current network architecture and we break it into parts. For example, here you see the LTE, so 4G architecture that has been modularized. And then we study the state variables and then study signals between different functions, different interfaces in this modularized architecture. And that way we can then start to do this refactoring. So we can then combine modules to meet the given goals. And here, for example, as our example, so we have the LTE, so 4G baseline architecture with certain signaling costs for these key network functions, features. We are then able to do this refactoring, and we are able to create, for example, a thin edge in which we have very simple base stations and most of the complexities in the network. And then we have intelligent edge in which we place most of the network functionality at the edge, so that the edge in a way is almost self-sustaining, highly resilient. And now looking at the signaling costs, so this intelligent edge actually now minimizes the signaling cost. So it has certain favorable properties, but the cost is that it has a lot of functionality now at the edge of the network. So this way we can study different kind of network designs, different ways of packaging network functionalities, and then be able to meet the application requirements in terms of resilience, signaling cost, latency, and so on. So it's a start here, and then we, of course, now would want to continue this line of research and apply this for 6G, for example. So that's one outlook that we have. So then, now considering security, so we of course would want to detect any security threats in our networks as soon as possible. And in this collaborative research, so we studied this problem, and we set out to detect anomalous IoT devices by looking at the network traffic. So basically, we do a fingerprint of the first packets an IoT device sends, and then we do the security analysis based on these fingerprints and on the network utilization behavior of the device. And we, as background, we have data from these different IoT devices, what are their typical behaviors, and this then allows us to classify these devices into different levels of isolation, so that we can, for example, trust devices that follow the patterns that we expect, and then if we see that there are anomalies, so then we kind of start to do this isolation of the devices that we cannot really fully trust these devices. And we implemented this, and it's a step towards having this kind of AI system for securing our networks. And this can be also, we deployed this with Wi-Fi, but this can be deployed also with 4G, 5G, and these technologies. And especially here, the O-RAN I mentioned is an interesting direction, because it enables us to obtain information from the RAN, radio access network, so that we could do anomaly detection with even more data from the wireless domain. So that's a very interesting direction for security research. But certainly security is a very important service that we can provide at the edge of the network. And AI has a very big role here for security services. Then, I would also now still want to mention two cases. So one is the industry case. And here you can see an overview of this, so that we have the central cloud, we have these deployments, and in this case we have studied the use of 6LoWPAN, so personal area network, to connect the different industry IoT devices, and then 5G for then connecting these 6LoWPAN deployments with the cloud. And we have different cases here. So one is that we first connect with the edge, and then the cloud, or directly connect with the cloud. And we have been studying the benefits of edge computing and looking also at the properties of 6LoWPAN for industry-oriented networks. And here, one takeaway is that the edge does have benefits, so that we gain latency by doing edge computing. So latency is really the key benefit, and as other takeaways, so we can conclude that 6LoWPAN works reasonably well for the industry cases, at least based on the empirical experiments we carried out. And we have been doing the experiments. So just highlighting one aspect of the experiment. So here on the right-hand side, top right-hand side, you see the latency of the sensors to the cloud and to the edge. And you see, of course, now a big gap here between the edge and cloud latency. So this is, in a way, the benefit of edge computing here. Enables us to really have a lower latency. And the application in this case has been anomaly detection with LSTMs for the industry data, especially power data and then HVAC related data. So then, so going beyond industry sensing, so we have also environmental sensing. That's really interesting as a scenario. And here we have studied the deployment of low-cost sensors and using AI to calibrate these sensors and process the data we get to produce pollution maps like this one. You can see here at the bottom right-hand side of the slide. And we have really some favorable results around the calibration aspect, so that we can really, by using ground truth data from higher quality sensors, we can then boost the capabilities of lower quality sensors and extend their accuracy and also capabilities. And just to show you that we created our own sensor device, so you can see it here. So this is a low cost, small form factor sensor device monitoring particulate matter, ozone, and some other properties. And we use edge-based AI to calibrate these and get to a reasonable level of accuracy for the air quality sensing. And we have been studying this as a kind of a long-term research activity. And now, so considering the 5G angle, so here we have two interesting considerations. So we have the low-cost sensors, and we are working on sensing as a slice, so that the network would accommodate high-density sensor deployments, and it's something that we can do with the machine-type communications support from 5G. And also mobile broadband can be used there as well. And then we are also studying hyperspectral cameras. So we extract air quality information from hyperspectral camera data. And there the images are very large. So there we have to have this mobile broadband support due to the bandwidth requirements. And we have been studying these. And as conclusion here for 5G, so we see that one size doesn't fit these different cases that we would want to have in environmental sensing. So we have very low data rates, but very high density of sensors. And then we have these really high data rates as well with the hyperspectral cameras. So it's a very kind of interesting scenario for 5G to then support because of these requirements. And we have been studying these. And now just to show you some results. So comparing 5G to 4G, so we observe in general this latency improvement that we didn't really observe so much throughput improvement when changing from 4G to 5G for the local sensors and for the cameras, but for latency we did see this significant improvement, 28% for the local sensors and then 17.6% for the cameras. And then we studied the use of edge computing and understanding the provisioning of edge computing for local sensors, air quality sensors, and then for the hyperspectral cameras. And here, of course, we know that edge matters. So as mentioned, so we get lower latency through edge computing, and then we also alleviate certain privacy challenges and data processing challenges as well by having a local processing of the data. But the provisioning then has many dimensions, and we observed in our experiments different trade-offs between CPU, GPU, RAM, and so on. So these are interesting takeaways when then considering a larger scale deployments of these systems. And this is something that we are now studying, that how to kind of support the scaling of these sensing deployments. And now the final point I want to mention about the deployments is the one we did with the network slice in collaboration with Aalto University. So we connected our local sensors to this slice, and then we experimented that how many VMs do we need to accommodate this growing number of sensors. So we did this kind of a scalability study. And we used a kind of baseline VM, so 4-core, 4 gigabytes VM, and then studied that what are the limits in terms of the number of sensors. And based on the experimental results, so we see this kind of a scalability limit between 10,000 and 20,000 sensors for this configuration. And then this has enabled us to study that now what if we want to scale to, for example, Helsinki-wide sensing system or take some other bigger city. So how many VMs do we need? And we have been now analyzing this. So let's say that we have two different configurations. So we have dense network with 400 sensors per square kilometer, and ultra dense network with 10,000 sensors per square kilometer. So then for the dense network, we need 9 VMs for the Helsinki area, and for the ultra dense network, we need 214 VMs. So we of course now see the cost of scaling here as well. And this is of course important that we understand also in a way the deployment characteristics of our systems, that how we use edge, how we use slices, and so on, to be able to provision the network and then ultimately generate the network that's optimal for this given deployment. And that's something that we see as a future direction. So now I'm ready to wrap up. Just to mention that we have the Edge AI Special Interest Group in Finland. So we have a community of researchers working on these topics, connecting 2 flagships. So the Finnish Center for AI, so FCAI, and then the 6G flagship led by University of Oulu. And we organize webinars, we organize events. So if you're interested, please visit our website and join the community. So it's a very exciting area, and many things are now happening. But now, thank you. And